Hello, everybody. I'm going to solve some of the questions, question 158, 160, and 164 for the calculus section in the course Maths 1151 at University of New South Wales. Now, here in this video, I will talk about the fundamental theorem of calculus and concept of antiderivative and how easy makes our life actually to use that concept when we are calculating certain integrals. Okay, this is a very important concept and you should expect as a part of your assessment. Fundamental theorem of calculus. The first one, there are two of them, two theorems of them that we have in this course. F is a continuous function on an interval a and b. And we define this integral from a to x, ft dt. The integral itself is a function of x, and we call them gx. And this is for all x's from a to b. If g is a continuous on a, then g is continuous on the interval, and it is differentiable. Then also the derivative of the gx is equal to f of x. Right? When you take the, so this theorem basically says that the integral and the derivations are in reverse operations some way. And the second part is makes many things are easier for us. If f is continuous on the interval, fb, fa, this is a capital F and capital F. And the capital F here is antiderivative of f, and the derivations of the capital F is a small f. Basically, this is j. I could use the j. So this capital F is the g function is defined in the first one. But this is traditional how we use. We use the antiderivative function as a capital, whatever this function name. This is f, so this is a capital F. And derivation of the capital F is that function. Okay, let's go through the problems and try to understand how we can use this theorem. We would like to, this question, find a function satisfying this condition for all t. We don't need to calculate anything at all. We are just going to use the theorem. So call this function gt. And this is a continuous everywhere because this is an exponential function. We know this continuous, and this is a rational function. It's continuous. And this is no singularity of the here. So it is continuous everywhere. Then we can apply the fundamental theorem of calculus 1. So by definition, gt from 0 to t fx dt. So the whole of this part will be a function depending on a t. And the t is the upper bound of the integral. Because of the fundamental theorem of calculus, it says that the derivative of this one is equal to that one. So if you take, so this is the function for RGS. If we take the derivative of that one, we will find f without calculating anything, without calculating integral, I mean. Okay, by taking the derivation of this function, so this is constant, so derivation will be 0. We have a rational function, so we need to take the derivation of this one times this, minus derivation of this one times this, divided by the square of the denominator. So that's what we are going to do here. E to the t will be e to the t, and then multiplying to denominator, minus derivation of the 1 plus 2t is just 2t, and the exponential of t, and the square of the denominator. So what we have here, e to the t, we have 1 minus 2t, t squared. So that's 1 minus t squared. And we have 1 plus t squared on the denominator. So that's the answer. That's the answer. We found the function f satisfying this condition. So this is f function. So yeah, the point is fundamental theorem of calculus are really helpful, and without calculating the integral, that's the idea. Without calculating the integral, you will find the results. Let's do the second example. So we would like to find out the limit of this integral. Now, let's say ft is e to the t squared, which is continuous everywhere. So we can apply, if we say define gx as an integral from 0 to x, e to the t squared dt, since we have the continuity everywhere, we can apply the first fundamental theorem of calculus, the first theorem of the fundamental theorem of calculus, says to us, g is continuous, differentiable, and the derivative of this is equal to f. And the derivative of the g is f. F is the e to the x squared, right? And then just substitute this knowledge to back. So we have limit x goes to the infinity, e to the minus x squared, and this integral. But this integral itself is e to the x squared. That's what we used by using the fundamental theorem of calculus. That's what I've seen. This observation here we can use directly. So that is just e to the 0. It is 1. Limit x goes to the infinity of 1 is just 1. So that's the calculation. That makes the life very easy. Okay, this question is about we will use the fundamental theorem of calculus, but also we will use the mean value theorem, and we will obtain this following result. F is continuous on the interval, and we would like to prove that there exists a C in between A and B satisfying this condition. So this theorem is very similar to the mean value theorem, and so we can view as this theorem as the first mean value theorem for integrals. We would like to prove this inequality. Let's see what we can do. So mean value theorem. This is just we know that mean value theorem from the previously, from the other classes. Just to remind ourselves, f is a continuous function on the closed interval, differentiable on the open interval. Then there exists at least one c. This should be interval here, sorry. An open interval, actually. Such that f prime c is equal to fb minus fi, b minus a. And we just seen first fundamental theorem of calculus. This is the second part that I need to use. If f is continuous on the interval, then the integral from a to b fx dx will be f capital Fb minus capital Fi, and the capital F here is the antiderivative of f, which means derivation of the capital F will give us f. So by using this theorem, these two theorems, I'm going to prove this equality. There exists a C satisfying this condition. That's the A. Okay, F is continuous on AB. This is given, right? This is given in the question, right? This is given. We start from here. Now, first use the first fundamental theorem of calculus part 2. That's its theorem. F is the antiderivative. F is continuous and differentiable because of the theorem. Now, use the mean value theorem. Mean value theorem, but this time for on the big ones, right? So, mean value theorem for the capital F. That's what we are doing here. Then there exists a C in the open interval such that capital C, F, capital F, derivation at C will be capital FB minus capital FA divided by B minus A. So take this B minus A onto this side, and FB minus FA will be the integral because of the calculus theorem. That's what we are going to do now. And observe that the derivation of this is since the capital F is the antiderivative, capital F derivation C will be FC. So that's FB minus FA is by definition, by the fundamental theorem of calculus, is this one. And that's the right-hand side. You take this one onto the left-hand side, and that's FC. It's FC, so that's cool of them is satisfied. Maybe I could write one more line, but I hope I hope this is clear for everyone. So this is FC. So FC minus B minus A, FB minus FA, which is this one, which is this one. So if you take the B minus A on this side again, that will be 1 minus A. Or you can think of that 1 B over A, FB minus A. So this is FB minus FA. So this is FC. I think this is clear from here. It is very straightforward. That's all for this video. I hope it is helpful for everyone. Thank you very much for listening.